Hey class, we're going to finish up the 5.7 notes today. I am on my tablet at home, so hopefully I can do my best here with this handwriting, but I believe we left off on this vocab slide talking about the difference between roots, solutions, factors, zeros, and x-intercepts. All very important vocabulary that mean just a little bit of different qualities when we're talking about characteristics of polynomials. So to start this off, roots and solutions are values of the variables such that, not too bad actually, using my finger here, such that the polynomial, I'm just going to say p of x is equal to 0. All right, so the difference between roots and solutions. Roots are from expressions of polynomials. That means no equal sign when the polynomial is set equal to 0. And solutions are actually equations. Okay. So when we have polynomials and we set them equal to 0, when we actually solve these for x, they're called solutions. When we just have an expression that's set equal to 0, those are classified as roots. One note I want you to put is that these can be imaginary, and we've actually looked at a couple examples with imaginary solutions. Can be imaginary. I'm just going to shorthand that there. Okay. Factors, on the other hand, that looks something like this. So we usually notate them with parentheses, and we have x minus some variable. I'm just going to call it a times x minus some variable b, and these themselves are what we call factors, right? When we have something in factored form, this is what it looks like. We break it down and undo all the distributing, all the multiplication. And when we looked at polynomials in factored form, we've graphed them in factored form. It's kind of nice because then when we go to find the x-intercepts, it's already factored for us, and we just have to plug 0 in for y. Okay, so these factors can't be imaginary. So make that note. Can't be imaginary. Factors cannot be. The only way we can get imaginary solutions is either by completing the square or using the quadratic formula. It's what we use if we cannot factor it. So that's an example of why factors cannot be imaginary. Okay, zeros are values of the variable such that the function, oops, oh, the function is equal to 0. Okay, so basically now if we're looking at these on a graph, where I have a function, I have like a y equals in front of it, or an f of x equals in front of a polynomial that makes it a function. When that equals 0, we call those zeros. And note, our zeros, even though we can't visually see them on a graph, these can still be imaginary. Awesome. Okay, and then x-intercepts, those are the ones we can visually see. So values of x where the graph crosses or touches the x-axis. Remember, it doesn't always have to cross in order to be considered an x-intercept. It could just touch it, like those repeated solutions ones. So this one with the graph crosses / touches the x-axis. Okay. And now we've talked quite a few times about this. If we visually see them, they're not imaginary, so x-intercepts can't be imaginary. Okay, so some big difference here. When the polynomial equals 0, we call those roots and solutions. As soon as we make it a function, meaning putting like y equals in front of it, those are classified as zeros, and x-intercepts are ones we see on the graph. So very similar characteristics here, but there are differences between these, and hopefully that kind of just lays out for you the key differences between those. And I'll keep using those vocab words too to help you put into context what they mean. Okay, this next example problem we're going to look at here. We are given the graph of a cubic polynomial, discuss terminology and what we know. So right away, in that first sentence, it says it's a cubic polynomial, so that means it's a degree 3 polynomial function. Looking at the graph, it looks like I have x-intercepts at -1 and 3. So let's list that. Again, even though it just touches there at -1, still considered an x-intercept. X-intercepts, x equals -1 and 3. -1, since it touches there, that is considered a repeated root. Okay, that's one thing I can tell from my graph. Since -1 and 3 are x-intercepts, I know those would come from factors of x plus 1 and x minus 3. So those are going to be somewhere within my polynomial. Again, picture those set equal to 0. Those would give us x-intercepts of -1 and 3, because that's what an x-intercept is when our output or when our y value is 0. And we practiced those problems last time too when we were going backwards, where I was giving you the solutions and you had to work backwards and write the factors and then multiply it all together. Those are some fun problems here. Okay. Looking at the end behavior here, well, we know it's a degree 3, so the ends are going off in two different directions. And since as x is approaching negative infinity, my graph is also approaching a negative infinity, and as x is approaching positive infinity, f of x is also approaching positive infinity. We would know this is a positive leading coefficient. And all it's really going to take is 1 point on our graph to find the actual equation here. So I noticed I have this nice y-intercept of 0, -3 located here. So we're actually going to go ahead and let's find the equation for this polynomial function. I'm going to try to write small here. So I could have some vertical stretch or shrink factor. I'm going to call this A. What I do know is I have factors of x plus 1, and I know that one is squared because I get that repeated root or repeated solution, and it also touches the graph there. And then I know I have that factor of x minus 3. So what we can do is we can plug in this point here, -3, 0, and we can solve for that a value. Okay. To save some time here and my sake of struggling with my tablet here, I'm going to tell you I got an a value of 1. So I know this equation would be x plus 1 squared, x minus 3. Okay, that's something else we know from this graph. One other thing I want to add that you will have to do in your homework. So let me quick erase what's on my graph here, if I know how to do that. Here we go. Okay, you are going to be asked this question right here to determine the number of positive real zeros, negative real zeros, and imaginary zeros, and explain your reasoning. That's what you're going to be asked in your homework. So when we're talking about positive real zeros, so that means x-intercepts, and positive meaning on this side of my x-axis. So for example, 4 would be a positive real zero. So if I were to list my number of positive, I'm just going to use RZ for real zeros, there would only be 1, and it'd be at x equals 4. Negative real zeros mean that they are located on this side of my x-axis, or simply just a negative x-intercepts here. So I have one of them at -1, so number of negative real zeros. Now, technically, since this is a repeated root, it counts as 2. Okay, so although it like visually only looks like we have 1, we do have 2. Now, our total number of zeros, and this is that fundamental theorem of algebra, this should always total or add to the degree polynomial. So since I have a degree 3 polynomial, and I technically have 3 x-intercepts here, my 1 at 4, that's my positive real zero, my 1 at -1, that's my negative real zero. Since it's repeated, it counts as 2. That means I would have no imaginary zeros. I'm going to use IZ for that. I encourage you to write it out. I just am struggling on my little tablet here. But so, for example, let me just say if you were to have like a degree 4 and there was only 2 x-intercepts and it crossed at both, so maybe it didn't count as like a repeated solution. If you had 2 x-intercepts but you knew this was a degree 4, the other 2 would have to be imaginary. This count right here of your number of real zeros, whether they're positive or negative, wherever they're located, the number of real zeros plus your number of imaginary zeros should always add or total what degree polynomial you have. Okay, so you'll have some examples like that in your homework to try. The only other thing I'd maybe point out here, talking about some terminology we know, is right here, this would be considered a local max. We talked about those before, meaning it switches from increasing to decreasing. I call those the peaks. And we'd have a local min down here where it changes from decreasing to increasing, or I call those like the pits and peaks. Okay, my friends, we got a couple of problems left here. Okay, verify the given zeros are actual zeros using synthetic division. Then list all zeros, including any not given. Okay, so I know that -3 is a 0. So if I do synthetic division, I should get out a remainder of 0. So I'm just going to start with that one because it's first on my list here. Okay, coefficients from the polynomial. 1, 2, 6, 18, -27. No placeholders needed. Okay, I'm going to do this fairly quickly. So remember, you bring down this, multiply outside, add inside. So here we go. Boom. Remainder of 0. So they didn't lie. That is a 0. Okay. So what that means is -3 is a 0. That means x plus 3 is a factor. And I technically divided it out of this degree 4 polynomial function synthetically. So I'm left with a degree 3 using the coefficients of my results here from the synthetic division. X cubed minus x squared plus 9x minus 9 is what I would be left with. Okay. Now you actually know how to factor this, and I would be a-okay in real life if you saw this and factored this by grouping and finished up the problem here. However, I just want to walk you through what if you didn't know how to factor that. Let's say we maybe just forgot how to factor by grouping and you're like, I don't know where to go from here. Here's your next option, especially when you're given another 0. So -3, okay, got that taken care of. Let's do this now, synthetic division with 1. Now, instead of using the original, we're going to use this result right here and try to factor out the x minus 1 factor from our remaining degree 3 polynomial function here. So let's do that. Again, I'm setting this up synthetic division again using these new coefficients. So I'm going to do this quickly again. Aha, another remainder of 0. Okay, so what that tells us, we still have that x plus 3 that we factored out already. Now we factored out x minus 1 from this 0. Cross that off my list here. And now, so I started with the degree 3 when I did my synthetic division. Now I'm left with degree 2. I'm left with x squared plus 0x plus 9. I'm not going to write in that 0x. Okay, so now this is fully factored. This is a sum of squares. It can't be factored further. So if I were to actually solve this, set these each equal to 0, you'll see what we get here. So we get -3, which is no shock. We are given that 0. We used it in our very first step. We get 1. Again, no shock there. We knew that. Here, I square root both sides. Don't you forget plus or minus. I get plus or minus 3i. And they did tell us that -3i was a 0. And we talked about this last time. Its conjugate, positive 3i, also is a 0, according to the complex conjugates theorem. And we found that algebraically right here. Okay, good stuff. So there's an example of when you're given a zeros, how you can use synthetic division to find all the other zeros. Okay, sometimes it's a little bit harder. Sometimes you're not given possible zeros. And I'm like, should I just start guessing random numbers? And I mean, you could, I guess, guess and check is a problem solving strategy. I wouldn't recommend it. What you're going to do, and you're going to do this in 33 through 38 on your homework, is you're going to use Desmos to help you pick a zero. All right, so let me pull up my friend Desmos here. And I'm going to type in this function. Y equals, let's see, x. I might have to use my keypad. Let me get my keypad plugged in here, folks. Here we go. This is way easier. Y equals x to the power 4 minus 6x cubed plus 9x squared plus 6x minus 10. Okay, so we're going to use this as a little hint of the possible real zeros. So I see I have two real zeros here, one negative, one positive, located at -1 and 1. So I'm going to use these to help me with my synthetic division process. So let's start with using 1. Boy, here we go. Okay. This problem is going to take up quite a bit of work here. Workspace. All right, let's start with 1. We know, according to our graph, that was a 0. Okay. I feel like I might need to make this a little bit. So again, bring down the 1, multiply on the outside, add on the inside. And bingo, the synthetic division checks out. It is a 0. Okay, so just like the last one, that means x minus 1 is a factor. And this started off degree 4, so this is going to bring it down to degree 3 when I divide out that linear polynomial. Okay, now here's a great example of this does not factor by grouping. You can try it, but it doesn't. If I factor on an x squared here, I'd be left with x minus 5, and there's nothing that I could factor out of that second group. That would leave me with an x minus 5. So we're going to have to do synthetic division again. And now I'm basically trying to break down this degree 3 polynomial function. And luckily, we saw on Desmos that there was another 0 at -1. So using the coefficients from the degree 3, let's finish this up here. Synthetic. And again, the synthetic division checks out. It is a 0. Okay, so what we know is x minus 1 is a factor. We know now x plus 1 is a factor from this guy. And we are left with x squared minus 6x plus 10 equals 0. Oh no, folks. Now, here's the bad news. This doesn't factor. There are not two numbers that multiply to 10 and add to negative 6. Uh-oh. How would we ever solve a quadratic that doesn't factor? If you're thinking quadratic formula, you are correct. Now, before we get in there, these are really super easy to solve. Honestly, you don't even really need to set them equal to 0. You can just tell me x would be 1 and negative 1. We found that with the synthetic division. But here, we're going to have to use the quadratic formula to solve this. Okay, so we know how to do the quadratic formula. I remember you guys doing fairly well on that quiz. So I'm just going to kind of quick plug everything in and then tell you what I get for an answer. Okay, so x equals negative b plus or minus the square root b squared minus 4ac all over 2a. Okay, so I got to this point from that. I know this is getting smaller and smaller for you to see, but hopefully you can kind of follow along here. I got to here, 6 plus or minus 2i, because I ended up getting a negative 4 under the square root. Don't forget to break this up for a final answer of 3 plus or minus I. And again, folks, there's another good example of anytime we get an imaginary solution, that it's always going to come in those conjugate pairs, right? And it comes from that plus or minus the square root when we have a negative under there. So you can see we had 3 plus I, 3 minus I, conjugate pairs, both imaginary zeros, imaginary solutions. Okay, that's all I have for you in the notes. Hopefully I will see you soon, and you can finish up the homework.